This is Algebra Lesson 4-4, Graphing a Function Rule. There are two different types of graphs that we're going to talk about today, continuous graphs and discrete graphs. A continuous graph is a graph that is unbroken, meaning the values between points are part of the solution, meaning you connect the points. It's like connect the dots. A discrete graph is a graph composed of distinct isolated points, meaning the values between points are not part of the solution. For example, let me show you what I mean. If I had a graph and we had a x and y axis here, and these were points, and I was working with a graph, and I had continuous points, like if I said the amount of money you earn from magazine sales, that would be a continuous graph because the points between the values have meaning, because you have so many cents between each value. I could make $12.05, I could make $12.20, but I have another graph here. Okay, and let's say I'm selling hot dogs. Okay, the number of hot dogs I sell. So if I go like this and I just put points on the graph like this, I can't sell half a hot dog. I can't. Somebody can't come up and say, "I'd like to order 3/4 of a hot dog, please," which doesn't work. So it's a discrete graph because the values between the points do not have meaning in that particular situation. And that's what's meant by the difference between a continuous graph and a discrete graph and a continuous graph. All right. The set of all solutions of an equation forms the equation's graph. A graph may include solutions that do not appear in a table. A table is a small snippet. The graph, because the graph can go on forever in either direction, most times, it should show points that show you everything. A real-world graph should only show points that make sense in the given situation. For instance, on my hot dog equation or problem, I only used quadrant 1 because you can't have negative numbers of hot dogs. Okay? No matter what you do, you cannot have a negative number of hot dogs. So therefore, it will always be points versus a line. All right, we're going to graph a function rule, and we have to make a table of values for each and graph these. When you go to graph these, it is really, really important that you understand how the table of values gets set up. Okay? The table of values gets set up in such a way so that you can use it to graph your graphs. Okay? I will require you, when you first learn how to do graphs, to give me a minimum of 5 points. On a linear graph, a graph that creates a line, you need 2 negative points, 0, and 2 positive points. And you always should go your negative points first, then 0, and then your positive points. If there is no fractions in your equation at all, like in problem number 1 here, I have y equals 2x minus 1. There are no fractions in my problem. So when I'm going to make my table, if I make my table here, I have an x and y table. Notice I leave some space in between my x and y. I do this for the main reason of I am going to need some space to show my work. You will need to do the same thing. Okay, so I sometimes write 2x minus 1 in here because it's helpful for me to figure out what I'm doing. Okay, so if I'm going to do this, like I said, since there are no fractions, I'm going to use choose to use -2, 0, -2, -1, 0, 1, and 2. Okay, because that's what I like to do when there are no fractions in my problem. So I'm going to use -2, -1, 0, 1, and 2. And all I'm going to do is I'm going to evaluate y when x is -2. And then I'm going to evaluate y when x is -1. So here's my work. I'm going to do -2, times 2. That is -4 minus 1 is -5. Okay. Then if x is -1, I should do it this way, 2 times -1, which is -2, minus 1, which is -3. When x is 0, 2 times 0, which is equal to 0, minus 1 is -1. When x is 1, 2 times 1, which is 2, minus 1 is 1. And last but not least, 2 times 2, which is 4, minus 1, which is 3. So these are the points that I'm going to plot on this set of x and y axes that I have down here. I should label my axes. Always label your axes. I will mark points off if you do not label your axes. Very important. Okay. Then we're just going to plot the points. I'm going to plot the point -2, -5 first. So I'm going to start at the origin, go to -2, down to -5, which is right here, plot that point. Then I'm going to go -1, -3. So start at my origin, left 1, down 3. 0, -1. Stay at my origin, go left and right, no points, go down 1. 1, 1. Start at my origin, go right 1, up 1. And last but not least, 2, 3. So start at my origin, go over 2, up 3. All of these points should make a line. If they don't, you messed it up. Okay, because this is a linear graph. I know it's a linear graph. I've told you it's a linear graph. This is where you need to use a ruler. I will be very picky on this if you don't use a ruler. You need to connect your points with a straight line. Okay, always connect your points with a straight line, because sooner or later we're going to have two graphs on the same set of x and y axes that we need to cross each other, and we need to figure out what point they cross at, and if you're not careful, you won't know. The last thing we need to do is we need to label our equation. You label your graph with the original equation, which was y equals 2x minus 1. That's how you solve a graph, by writing a table and graphing it. If this was a problem in your homework, you would get 5 points for the table and 2 points for your graph. They always put your arrowheads on the end of your graph, because this is telling you that your graph is going forever in that direction and forever in this direction, which means the table of values is a small indication of what the graph actually is. The graph goes on and on forever, so the graph shows me more answers than the table does. Let's look at this second problem here. Y equals -1/2 x plus 2. Now, when you have a problem in which the equation is, it's a linear equation, because there's no power of 2, and there's nothing else. There's nothing that tells me that is a not linear equation. I will tell you how to figure out if it's not linear. So this is a linear equation, but it has a fraction in it. Nobody likes to deal with fractions. Fractions are annoying. Most people like to avoid them. So what I tell my students to do is, whenever you have a fraction, when you have a fraction here and no fraction here, you are going to look at the denominator of the fraction, and you're going to pick multiples of that denominator for your x and y table. I'm going to move my x and y table up here so it will fit in nicely. What do I mean by multiples of my denominator? I've got -1/2 x plus 2. Well, what's 2 times 2? It's 4. So I'm going to start with -4, -2, 0, 2, and 4. I'm just taking multiples that, when I divide them by 2, are divisible evenly, so I don't have fractions in my answer. So here's my workspace. -1/2 times 4 over 1. Okay, -1/2 times, -4 over 1. I almost messed that up. Half of -4 is -2. So I have -half of -4 is +2. So I have 2 plus 2, which equals 4. Then I'm going to have -1/2 times -2 over 1. Half of 2 is 1. 1 plus 2 is 3. Then I'm going to have -1/2 times 0. Anything times 0 is 0. 0 plus 2 is 2. Then I'm going to have -1/2 times 2. Half of 2 is 1, but negative of that is -1. So -1 plus 2 is 1. And then I'm going to have -1/2 of +4. Half of 4 is 2. Make that negative. It's -2 plus 2 is 0. Notice how all my answers ended up to be positive whole numbers, or excuse me, just whole numbers rather than fractions. Hey, I'm going to graph these points on my lovely set of x and y axis down here. I'm going to label it again. X, y. Start at my origin. -4, +4. -4, +4 is right there. And I'm leaving -2, +3 is right there. 0, 2, right here. 2, 1, right here. And 4, 0, right there. Get my handy dandy ruler. Mine's a little different than yours, because I'm special in that way. Okay. Draw my handy dandy line, which I missed massively, and I'm going to fix in just a second here. Okay, now make sure my line actually goes through my points. There it is. And the last thing I need to do is make sure I label my equation. Y equals -1/2 x plus 2. It's really important that you make your tables easy for you. So if you have a fraction, you should use multiples of the denominator. So if my fraction was 1/3, I would use -6, -3, 0, 3, and 6. If my fraction was 1/12, I would use -24, -12, 0, 12, and 24. I use multiples of my denominator to try to solve the problem. That eliminates the problem of having fractions in my answer. All right, when you graph a real-world function, choose appropriate intervals for the units on the axes. Each interval on the axis should represent the same change in value. I talked about this before. So on my x, if I'm counting by ones on my x, I need to make sure everything counts by ones. And on my y, if I count by fours, it has to go by fours. I can't count one interval by 4 and the next interval by 12 and the next interval by 6 and the next interval by 2. Okay, if I'm counting by fours, I count the whole thing by fours. If I'm counting by twos, I count the whole thing by twos. That's a really important rule that you need to understand. All right, so let's graph a real-world function. It says, the function c equals 12.5h plus 30 represents the total cost of renting a truck for h hours. What is a reasonable graph of the function given that the daily limit is 12 hours? So the longest you can rent the truck is 12 hours a day. Okay, so that's the most number of hours that we need to use. Okay, so first thing I'm going to do is I'm going to make a table. So I have hours, cost. Okay, and we know it's 12.5 h plus 30. Okay, so if I don't rent the truck, if I don't use the truck at all, I want to rent the truck, but I haven't used it any hours at all, I'm going to have 12.5 times 0, which is 12.5. Add 30 to that, and it's going to be, 12.5 times 0 is not 12.5. Wow, that was bad. 12.5 times 0 is 0. 0 plus 30 is going to give me 30. You don't necessarily have to graph by ones. I'm not going to graph by ones. I'm going to graph by twos. Okay, I'm going to jump in 2-hour intervals because I'm going to be in the middle of them. It's fine. So I'm going to do 12.5 times 2, which happens to be 25. 25 plus 30 is 55. And I'm going to go for 4 hours. If I rent it for 4 hours, 12.5 times 4 is going to be 50 plus 30, which will equal 80. And then if I have 5 hours, excuse me, 6 hours, I'm going by 2 hours, and I just said that, and then I messed it up. So then it's 4, then it's 6 hours. 12.5 times 6 is going to be 75 plus 30, which is 105. And if I go 8, 12.5 times 8, it's going to be 100 plus 30, which is 130. Now, I don't have to go forever. I don't have to go all the way up to the 12 hours that you can rent it for the day. I just need to get an idea so that I can start graphing my graph. Now, because I know I cannot rent a truck for a negative number of hours, and I know I cannot give them a negative amount of money, I only need quadrant 1. So all I'm going to do is give myself quadrant 1. So there's my x-axis on quadrant 1. There's my y-axis on quadrant 1. Okay, so my x-axis is my time in hours. Okay, and I'm going to count these by ones. 0, 1, so there's 2, 3, 4, 5, 6, 7, 8, 10, 12, 14. I don't even need to go to 14 because the maximum amount of hours I can rent it in a day is 12 because they want it back at night. You can't rent it overnight. Okay. And then money-wise, I'm looking at this going, ooh, 30 to 130. I probably don't want to count by twos because I don't have enough squares to count by twos. Okay, this is my cost. It's going to be in dollars. So I'm thinking maybe I'm going to start counting by, oh, let's see here. 10, 20, 30, 40, 50, 60, 70, 80, 90. Nope, 10s probably aren't good enough, so I'm going to go by 20s. 20, 40, 60, 80, 100, 120, and 40, 160, etc. So now I can graph this. If I rent it for 0 hours, it's going to cost me $30. $30 is halfway between 20 and 40, so it's right there. If I rent it for 2 hours, it's going to cost me $55. 40 here, 50 is halfway, 55 is barely over halfway. It doesn't have to be perfect, but it's going to be pretty close. Okay. No. Yeah, 2 hours is 55. 4 hours is $80. So 4 hours go up to $80. That would be right about there. 6 hours is 105. 100 is here. 105 is just a bit above it. 8 hours is 130. So go up here and go to 120 is here. 140 is here. Halfway between is here. Okay, this should make a nice straight line. Okay, this is still what I would consider to be a continuous graph because the values between them is still going to cost me money. If I rent it for 5.5 hours, it's still going to cost me money. Okay, it's still going to cost me money if I rent this truck for 5.5 hours versus 5 hours. The half-hour increments do count. Even the quarter-hour increments probably count. So there's my graph. And of course, I didn't put my arrowhead on it, so I now need to put my arrowhead over here. There we go. And of course, I should label it. C equals 12.5H plus 30. So now I could make a prediction. Okay, if I did this right, if I rented the truck for 10 hours, okay, if I go up here in my lovely little thing, 10 hours should cost me about 155 to 160. Okay, and it's on 160. It's a little off. It's probably a 155 closer. But there you have the graph of a real-world function. Real-world functions, you have to think about what the values are of things. Like I can never rent it for a negative amount of time, nor can I spend a negative amount of money. Therefore, I don't need anything but quadrant 1. All right, so here's a key concept, continuous and discrete graphs. Here's a continuous graph is a graph that is unbroken. A discrete graph is composed of distinct isolated points. Okay, so let's take a look at a question here. It says, identifying continuous and discrete graphs. Megan buys eggs at the supermarket for $1.75 per carton. The cost is a function of the number of cartons bought. What is the graph of the function, and is the function continuous or discrete? Okay, so if she buys them for $1.75 a carton, so I have N, and I have C, which is my cost. Okay. And they're going to cost me $1.75 a carton. I can't buy part of a carton. I have never been able to go into the store, open a carton of eggs, and say I want 3 of them out of the carton. They tend to frown upon that in the grocery store. They tend to think you're a little weird, and then they tell you to put all the eggs back in the carton and buy the whole carton. Okay, so I'm going to spend $1.75 a carton. So my function is going to be 1.75n. So if I buy 1 carton, it's going to be 1.75 times 1, which is $1.75. If I buy 2 cartons, it's 1.75 times 2, which is going to be $3.50. If I buy 3 cartons, 1.75 times 3, which is $5.25. If I buy 4 cartons, it's 1.75 times 4, which is going to be $7. And if I buy 5 cartons, it's 1.75 times 5, which is going to be $8.75. Okay, so I'm going to start graphing this. I can buy a lot of cartons of eggs. I mean, it depends on how many eggs I need. Maybe I need a lot of eggs. Maybe I like eggs. Maybe I really, really, really like eggs, and I want to buy, 100 cartons of eggs. I'm going to make a lot of eggnog. Who knows? Okay, so I'm going to graph my x and y axes here. There we go. Label them x, y, or in some cases, in this case, I don't even have to label them x and y. I should label them n and c, shouldn't I? Because this is n, number of cartons, and c, this is cost. And I should label my graph accordingly. So this is going to be number of cartons. And this is going to be my cost in dollars. Okay, my number of cartons is pretty easy. I can graph that by ones. So this is 0, this is 1, there's 2. I'm graphing every other one because it's easier to label. Now my money, I probably should go by whole dollars. Okay, $1, $2, $3, $4, $5, $6, $7, $8, $9, $10, $11, $12. That'll probably be fine. Okay, I'm going to graph my points. So if I buy one carton, it's going to cost me $1.75, which is approximately there. If I buy 2 cartons, it's $3.50. $3.50 is halfway between 3 and 4. 3 cartons is $5.25, so we'll go up to 5. $5.25 is about there. 4 cartons is $77. 4 cartons up here to $7, which is right there. And 5 cartons is $8.75, which is about right there. I do not draw a line for this data because it's definitely discrete data. I can't buy part of a carton. We talked about that. If you go into the grocery store and you want 3 eggs out of the carton, they're going to look at you funny, and you don't want that. So this is a discrete graph, as you can't buy part of a carton. So there we go. Okay, now, I did say that sometimes that you will have things that are nonlinear functions. The function rules we've graphed so far have been linear. You will also graph nonlinear functions. When a function rule does not represent a real world situation, it is a continuous function. Okay, so let's look at some nonlinear graphs that we're going to graph. If we get up here, we have what is the graph of each function rule? Y equals x squared minus 1. This is a nonlinear graph. Nonlinear graphs are to a power other than 1, or they're absolute value graphs. All exponential graphs, graphs to a power other than 1, and all absolute value graphs are not linear. This is important. It's important to know. So when you have a nonlinear graph, you must graph at least 5 points, sometimes 6 or 7, to figure out exactly what the pattern was looking like. So be ready to graph more points than usual. All right, so let's see here. Let's do x and y, and we have x squared minus 1. I'm going to use my famous -2, -1, 0, 1, and 2. That's probably enough spots for me to be able to graph this. So I'm going to have -2. Notice how we square that. It has to be in parentheses squared, which means it's going to be a positive 4. 4 minus 1 is 3. -1, whenever you substitute something in for a square, it always goes in parentheses. So -1 squared is 1. 1 minus 1 is 0. 0 squared is still 0. 0 minus 1 is -1. 1 squared is 1. 1 minus 1 is 0. 2 squared is 4. 4 minus 1 is 3. And you might look at that and go, wow, that's some weird points I'm getting. So watch what I do. This is a nonlinear graph, which means we're not going to play connect the dots like we did when we were younger, because it'll look like a really weird graph if you play connect the dots. So let's graph. -2, positive 3 is here. -1, 0 is here. 0, -1 is here. 1, 0 is here. And 2, 3 is here. This is what we call a parabola. And we want to graph it with a smooth curve. It looks something like that. We don't play connect the dots. It's a nice little curved graph. And y equals x squared minus 1. The more you do these, the better you get. Of course, don't forget to label your x and y axis, which I almost forgot to do. Okay. And there we have our graph. And it's a nonlinear graph. It's not a straight line graph. It is a smooth curve. All graphs to the power of 2 will be what we call parabolic graphs, or a parabola, and it will be a U or an upside down U. Okay, they will all look like this U. It may be a skinnier U, or maybe a really wide U, okay, or maybe an upside down U. But all graphs that are taken to the second power, x squared, will be a U-shaped graph or an upside down U-shaped graph. Number 2 here, y equals the absolute value of x plus 2, is an absolute value graph. All absolute value graphs have a distinct shape as well, which you will be able to figure out once we've finished actually graphing this one. We'll talk about it. Again, since we don't know what the shape is, you will eventually, you should always pick at least 5 points. At least 5 points. Since there are no fractions, -2, -1, 0, 1, and 2, my famous happy points. I've got the absolute value of x plus 2. So this says, take the absolute value of -2, which is 2, plus 2, which is 4. And I'm going to take the absolute value of -1, which is 1, plus 2, which is 3. Then we're going to do the absolute value of 0. Absolute value of 0 is still 0, plus 2 is 2. Absolute value of 1 is 1, plus 2 is 3. And the absolute value of 2 is 2, plus 2 is 4. So we're going to graph these graphs, these points. So -2, +4 is here. -1, +3 is here. 0, 2 is here. 1, 3 goes there. And 2, 4 goes here. If you can see this, this is a V-shaped graph. Okay? This is a V-shaped graph. It goes like this, and then it goes like this. Okay? All absolute value graphs are V-shaped graphs. They'll either look like this, or they'll be upside down looking like this. Some of them will be very skinny. Others of them will be very wide. But all absolute value graphs are V-shaped graphs. Last thing we need to do, label our axes and our graph. Y equals the absolute value of x plus 2. So we have now graphed linear graphs and nonlinear graphs, continuous graphs and discrete graphs. All right. It's a lot of graphing, I know. Your closure question, how can you tell whether or not to connect the points on a graph with a line or a portion of a line? In other words, how do you tell whether or not it's going to be continuous or discrete? That's your question to answer at the end of your notes, please.